Welcome to Maths with EJD. In this video, I'll be talking about advanced broadcasting in NumPy. So I'm navigating my way to Jupyter Notebook. And of course, you should know that the notes are available. If you check the description box, you find a link to where you can download the notes. So you can get the notes downloaded and then follow so you can learn hands-on. So my folder is on the desktop, so I navigate there. And this is the 13th video under scientific computing with Python. And today our focus is on advanced broadcasting. So it's an extension of what we did previously. All right. So we already know broadcasting is doing something over an array without having to loop. All right. So for advanced broadcasting, I'll just talk about some examples and see the applications, and then this video will be done. So first of all, let's talk about subtracting mean across rows. So you are subtracting the mean of each row from the respective row. For instance, you have A now. A is actually an array of a list of lists, right? You're making a NumPy array from a list of lists. So you have 3 rows and 3 columns. One, row 2, row 3, and then 3 columns like that. So of course you can already expect. Okay, I mean, let me print that so you can see exactly what that is. So it's a 3 by 3 matrix with numbers 1 to 9. So print A there, then print blank so we can have some space. Then you want to do the row mean, and the row mean is a dot mean axis 1 equals keep dimensions true, and the shape is 3 by 1, and we have this printed. Then we're also doing this blank print so we can have some space. So let's see how this goes. So I run that and see all that we get. Of course, this is A itself, 1 2 3 4 5 6 7 8 9, and then we are doing the row mean. So we are doing mean by row. That means you are actually saying 1 plus 2 plus 3, that is 6 divided by 3, that gives you 2. And 4 plus 5, 9, plus 6, 15 divided by 3, that's 5. 7 plus 8 is 15 plus 9, 24 divided by 3, that's 8. So because we are doing row mean like that. So the next thing we are doing is we are subtracting this means from each row. So from row 1 now we are subtracting 2. So 1 minus 2 is minus 1. 2 minus 2 is 0. 3 minus 2 is 1, like that. And then of course 4 minus 5 minus 1. 5 minus 5 0. 6 minus 5 is also 1. Then same thing for the last row. 7 minus 8 minus 1. 8 minus 8 0. 9 minus 8 is 1, like that. So we are subtracting mean across rows. And another thing you can do is to add a vector to each row of a matrix. You want to add a vector to each row of a matrix. See how that goes. So you have A, which is 1 2 3 4 5 6, and then you now have, and that is actually a list of lists. So it is going to be a 2-dimensional array. That's 2 rows, 3 columns. But here it's just 1 row, 3 columns, and we want to add this vector B to this array. I think we've done something like that in the previous one. I mean, just to mention this again. So basically what is happening here is 1 2 3 is added respectively to 10 20 30. That's why you have 1 plus 10 11, 2 plus 2 20 22, 3 plus 30, that's 33, and then the same thing goes for 4 5 and 6 added to 10 20 30. So we've had an example like this under the previous one. Then what about using broadcasting for outer product? So broadcasting for outer product. So here you have a 1 by 2, and then you also you have a 1 by 3 array, and here you have a 1 by 4 array. Guess what? You have 1 by 3, and then you now have 1 by 4. So, but then we are doing outer product. So in this case now, so for A now, you have, so you have np.new axis multiplied by B. So what is going to happen here is that you have 1 multiplying through, and you get 1 row. You have 2 multiplying through, you get another row. 3 multiplying through, you get another row. So that way you now finally have a 3 by 4 matrix coming from a 1 by 3 and a 1 by 4, because we are doing outer products. And that's why this NP new axis is like the trick thing right here. So if you do that, see exactly what you get. Okay, so we can also talk about complex broadcasting with higher dimensions. So you have, I think I've done this before. this is going to be a 1 by 4 in 3 places. 1 row, four columns in 3 places. This is 5 rows, 4 columns in 4 places. I mean, in 1 place, actually. And then, okay, in fact, let me try to print that so you can see what is happening right there, because what this result will be giving us is just the shape. So we want to see the actual thing before we see its shape. So let's print B also. And then, yeah, so do a blank print blank, and then we have print AB, and then print the results and print blank. Then we now see the shape is 3 of 5 by 4s. Now you already know 1 by 4 and 5 by 4 is definitely going to give us 5 by 4. But then out of 3 and 1, you are going to have it. So the higher number dominates. So you have a 5 by 4 in 3 places, and that's exactly what we are going to have. So look at this first one is 1 by 4 in, so 3, 1, 4. That means 1 by 4 in 3 places. This is 1 by 4, 1 by 4, 1 by 4. Just 3 of them. The next thing is you have 5 by 4 in 1 place. So you can see this is a 5 by 4 matrix. This is a 5 by 4 matrix. And of course, these numbers are random. If I run it again, you see the numbers will change. The numbers are random, as you can see. So for instance, this is 826, 5192, 1345. So if I run it again, because of this random stuff, right? You can see the numbers keep changing like that. All right. But when we add the two together, right, we expect to get 5 by 4 in 3 places. And that's why you now have all this 5 by 4. That's 5 rows, 1, 2, 3, 4, 5. And you have that in 3 places. And that's exactly what's happening. So you can see the shape. It's 3, 5, 4. So 5 by 4 matrices in 3 places. And that's what happens right there. So you can actually play with all of these things as you find them applicable. So let's look at the practical applications. Now, in image processing, I hope you know that most of these things we do, image processing, sound processing, and all those things. Sometimes these things are basically matrices, especially when you talk about image processing and vision. What's that thing now? Computer vision. They are mostly matrices you're playing with. So, for instance, one simple thing in image processing is about this idea of applying a filter. Apply a filter to an image represented as a 3D array. So, you see, you have this image. So, of course, you have so many. And that's why when you're dealing with images, right, you need a lot of data. So you can see you have a 256 by 3 matrix in 256 places. That is a whole lot. In fact, I won't even bother trying to print that because that'll be overwhelming. And then you now have a filter that you want to apply to it. So you have 0.1. So to the image now you multiply each corresponding element by 0.1, 0.2, 0.3 correspondingly. And then so you now have the filtered image will now be the image multiplied by the filter. And then you can now print the filtered image. And then I'm giving a space. So the filtered image is going to be a whole lot, right? Because you are going to have you have 256 of 256 by 3, right? And this is 1 by 3. So you're definitely going to have 256 by 3 in 250. So the dimension is going to be the same as the dominating one. So if I run this, see what you get. Plenty. So you can see all these breaks in between. Shows you that there are so many of this because you have 256 by 3 matrices by 3 matrices in 256 places like that. So that's how that goes. Okay, so I mean, if you work with image processing, computer vision, you can find this very useful. And then we talk about data standardization. So the other time we talk about data normalization, right? And this standardization too is, in fact, it's about the same thing like what we talked about the other time about normalization. So you have here, you have a list of lists, which gives you a 3 by 3 NumPy array. And then, of course, we find the mean. Then, of course, we find the standard deviation. Then you standardize. So it's just like the normalization previously. So it's about the same procedure. Axis 0 means 147. So 1 plus 4 plus 7, that's 1 plus 4 is 5, plus 7 is 12, divided by 3, you have 4, right? And then you have 2 plus 5, 7 plus 8, 15, divided by 3, you have 5. And 3 plus 6, 9 plus 9 again. That is 18 divided by 3, you have 6. That's for the mean. And for the standard deviation, you have these 3. And then what you're doing is you're multiplying each data you have, you're subtracting the mean from it, and then you're dividing by the standard deviation for each case. So, and then you get all of these values. Now you see that the middle ones are always 0 because it's normal. 2 minus, is it the middle ones now? Yeah, okay, like the first ones. So, I mean, it ends up giving you 0 in the second row in each case, like that. So for the 4, 5, 6, now you see the second row is 4, 5, 6. So you have 4 minus 4, 0, 5 minus 5, 0, 6 minus 6, also 0. All right, so that takes us to feature scaling. Now, some of these things happen in maybe different areas where you may be applying Python. So scale features in the data set to a range 0 to 1. Now, one way, like if you, for instance, whenever I teach data analysis, right, we get to that point where we talk about, how to clean up your data or how to make your data suitable for analysis. So part of what we do there is scaling, right? So you probably want to scale your data. So whatever the data is, you want to scale it to lie between 0 and 1. And that way it's easier to use for your analysis. So here now we have a 3 by 3 matrix again. So the minimum of the values we want to get, then we want to get the maximum of the values, and then we want to scale. Because for scaling, right, you need whatever data you have. It's like you have x minus x mean minus maximum x minus minimum x, something like this. And that's what exactly is happening here. So you have data minus minimum value divided by maximum value minus minimum value. That way, you can be sure that whatever data you have, it's between 0 and 1. So that is scaling. So those are the two things we do and what some of the two techniques we can use sometimes to make the data conform into one place. For instance, if you want a normalized data, you can do that. You need the mean, the standard deviation, such that the data is normally distributed. And in this case, scaling is just to make sure that the data is always between 0 and 1. So you see, after doing all this all this process, right, everything ends up, falling between 0 and 1, like that. So that's what feature scaling is about. So normalization and scaling are two important things we do in data analysis to be sure that the numbers are within a particular range. Okay, so finally, let's talk about broadcasting in machine learning. So, for instance, you want to compute the Euclidean distance between each pair of points in two sets. So you have the first set is a 3 by 2, and then you have the second set, which is a 2 by 2, So at the end of the day, of course, you expect to get a 3 by 2 because the dominating row is 3, and for the column, it's 2, so it's just going to be normal 2. So you want to find the distance between this pair of points, right? And of course, this is the formula. Okay, for the view now, go to show line numbers, right? So in line 3, if I push it down, it's line 4. So you have the formula right there. So it's like this whole idea of the distance between 2 points, and that's like maybe square root of x squared, the absolute value of x minus y. That's one way to look at it, which is like sometimes like the square root of x squared plus y squared minus z squared or something. And each of those are like the distances, the difference squared, like that. And that's what the formula is. So if you do that for this set now, you end up getting these values like that. And with this, we come to the end of advanced broadcasting, which is also the end of NumPy. Of course, there's so much more you can do with NumPy. NumPy is all about arrays, and of course, we've seen how to index these arrays, how to slice these arrays, how to reshape these arrays, how to manipulate the shapes of the arrays, and how to broadcast. So from the next video on scientific computing, I'll be talking about SciPy, which is another very powerful library in Python for scientific computing. So if you have not subscribed, you don't want to miss what is already there for you to learn from and what you have ahead. And to make sure that happens, be sure to subscribe and of course hit the notification bell so you can get an alert each time a new video is uploaded. And of course, don't forget to comment, like, and share. Part of the comments can be what you like to see. Maybe there's something you like to learn maybe in Python or in mathematics, or I mean, you can look around this channel to see the various things we get to do, and you can take part in those activities by making a request. Thank you so much for listening. See you on the next one.